Hi, in this video, we're going to take a look at factorial designs, principles, and applications. All right, so factorial designs are going to be like our exhaustive approach to cover the full range, all combinations of possible factors that we've got going on. All right, so what we're going to do, we're going to identify factors that we believe to be important in our situation and ones that we can measure and control for the purpose of the experiment. And then what we're going to do, let's say that we're talking about like wing length or something like that. I'm going to pick two values of wing length, one that's like larger and one that is smaller. And when I say larger, on the extreme end, reasonable but still extreme, and then short, reasonable but on the short end. And I'm going to do that kind of thing over and over and over for all of the different factors I have got going on. And then a full factorial design, I'm going to go through and run through all possible combinations. Now, if you think about that, that can be a lot of data that we're going to generate. That can be a problem. We'll talk about ways to get around this when we get to partial factorial design. But for the moment, we're baby stepping into it. We're talking about full factorials, keeping it simpler first, that we're going through the whole full range of possible combinations. All right, so first let's review randomized block designs. In randomized block designs, each block contains subjects that are similar in some way, and each subject within a block is exposed to only one treatment level. Now, in this, a block is what's coming to us in a way that we can't control. So imagine that I'm going to have some testing on all students at my school. Whatever gender they are is the gender they are. I don't control that as an experimenter. What I can do, I can separate into groups, but when it comes to the actual experiment, I don't have control over that. We use blocking to deal with this. Now, randomization block designs enhances experimental precision by controlling for variability within groups of similar subjects. Now, also with randomized block designs, we might not even have randomized. It might be just because of logistics, because of the situation I'm in, like we're at a school, we're at a business, a factory. We don't have the option from the logistics point of view to do random assignment. So it might be a non-randomized block design. Remember that poor experiments and poor data science are usually better than no data science at all. And so if you get into this position, don't cause a problem, don't get mad, don't get angry. If you're trying to submit for an academic paper, though, you need to have the highest rigor in your experiments possible. Now, full factorial designs. Now, if you hear factorial design, that implies full factorial. That's all possible combinations. Partial factorial design, it means that we have a subset of those. And we'll talk about how to get the best subset possible in future videos. All right, the primary aim of factorial design is to investigate the effect of multiple factors and their interactions and their outcomes. So I'm going to have multiple factors that I'm interested in. Factorial designs require each experimental unit to be exposed to all possible combinations of treatment levels. This means that I can end up having like a lot of data. Imagine if I have just two levels of all my factors. Well, if I do, so if I just have one factor, that's going to be 2 to the power 1, 2. If I have two factors, then that's going to be 2 to the power, 2 to the power 2, 4. And then if I'm going to have another factor, 2 to the power 3, 8. And you can see that this grows very rapidly. And so it's going to end up that we can result in a lot of data. Factorial designs are particularly useful in complex scenarios with multiple factors influencing the outcome. Full factorial designs require more observations than other experimental designs, and also more distinct observations. So all the levels are different, and typically, when we get into a lot of factors, we won't even have the option to replicate just because of time, money, and effort. All right, so typically, full factorial designs are used when we only have a few factors to study, like 2 or 3. Partial factorial designs use abstract algebra to use less data and reach comparable results. Of course, I would want the full mamma jamma if I could, but we can reduce this down and get comparable results. We'll talk about partial factorial designs down the road. All right, so understanding factorial designs. The purpose is to study multiple independent variables factors in one experiment. We're going to test every combination of factor levels possible. So if I have 3 factors, 2 levels each, that's 2 to the power of 3, 8 different distinct levels are going to be going on. And the outcome is discover the direct effects and interactions between factors. All right, so let's go ahead and do an example. So let's say that factor 1 is light conditions. So we have full sunlight and partial shade. We have fertilizer type of synthetic or organic. And so off of this experiment, I have 4 distinct possibilities. And my response variable is the growth in centimeters. Okay, so what I'm going to do, I'm going to set up my experiment. Okay, so I'm going to go through and I'm using Python to execute using pandas to get a data frame. And so here, what I'm going to do, I'm going to do 20 replications of each level. So I've got 4 distinct levels. That is full sunlight, synthetic, full sunlight, organic, partial shade, synthetic, partial shade, organic. 4 possibilities. Now, to improve my experiment, I'm going to replicate these 4 levels 20 times each. Okay, and so I'm going to have an ID number in my data frame. I'm going to have the light condition, which is full sunlight or partial shade. I'm going to have the fertilizer, which is synthetic or organic, and then I'm going to repeat as needed. All right, and so now, now something I did here is that notice that I'm leaving this blank. All right, so these are what I have on the screen right now are the aspects that we can control. That this is we're setting this up, and we're conducting our experiments, and we're interested in the relationship between light and fertilizer and growth. And so the growth result is going to be the dependent variable, the response variable to the other 2. And this is what we want to study. So I'm going to go conduct the experiment. I'm going to measure the growth, and then I'm going to record it on my data frame. Then I do my analysis. Okay, so here what I'm doing, I am pretending that I'm going out conducting the experiment over some time span. I'm growing plants. I measure the growth, and then I take a look. I'm using random normal generation to generate each of the different levels, just to give you an idea of what this will look like. But in real life experiments, this chunk of code here is actually conducted by going out with some measurement tool and measuring what's going on, and I get my actual results here. All right, so when I get my data, notice that I've got 3-dimensional data going on. I've got growth is my primary interest, light condition fertilizer type. I know that those are like 50-50. I set up the experiment. I'm not going to, I might do a visualization for my stakeholders, but I'm really not that interested in it. So the first thing I'm going to do, I'm going to analyze growth as a univariate variable by itself. And I'm not even going to consider the covariates. And so, always start simple and progressively get your analysis more complicated as you go. So I'll go out, I'll do my summary statistics. I like box plots a lot. It's a 5-number summary. And so here is my box plot. So I can see, the interquartile box. So here the, Q1 is maybe like 17-ish. Q3 is, let's say, maybe 28. And I've got maybe 23 as the median value. And, things look, relatively pretty symmetric. Okay. Now, let's go ahead and now, after I do univariate, I'm going to consider one independent variable at a time in my analysis. I want to see what's going on. And so now I'm going to consider light condition. So in my box plot, I'm going to have, and how you analyze this will depend on your hypotheses of what's going on. I could definitely do a hypothesis test. I could definitely do other visualizations. I'll do whatever works for my field, for my stakeholders. And so I've got full sunlight and partial shade. And now this data was by random number generation. Don't trust this to reflect actual plant growth. This is just I just arbitrarily threw down numbers. Don't worry. So in the parameters of the random normal. So don't worry too much about the interpretation. I just want to have this as a placeholder to show you what's going on, because I'm pretty sure that partial shade would not result in more growth. But let's pretend that this is real data. Okay, if I see like big difference between the box plots, specifically the interquartile boxes, that is evidence that there's something going on between growth and sunlight. All right. And so, specifically, I'm going to look at the median lines and see if they don't cut horizontally into the box of the other one. If I see the boxes are completely different, that's strong evidence for there's something going on. If they're perfectly parallel, that's evidence that there's nothing meaningful going on. And here we have like a little bit of a bump. And so it depends on our sample size, honestly, at this point when I look at this. All right, so now let's go ahead and take a look at fertilizer type. And now I've got synthetic and organic. All right, so something that jumps out at me immediately is that synthetic has much greater spread than organic. Now, this is fake data, random number generation from me. This doesn't reflect reality, but if I see this box plot right here, I go, hey, it looks like there's a difference in the spread between synthetic and organic. Now, I see that the median lines are cutting into each other, and the boxes are pretty much like middle part next to middle part. So that's an indication that in terms of growth, they have about the same average, but synthetic, this gives me evidence that has greater spread, greater variability. So now let's go a little bit deeper into this. All right, so I started with univariate analysis. Then I do bivariate analysis on each independent variable with the response. Now I'm going to start kicking it up a notch, and I'm going to try and go deeper. Okay, so now I've got my 4 box plots. Blue means it's synthetic. Orange means it's organic. The full sunlight's on the left. Partial shade is on the right. Okay, so I see that I've got a synthetic. Partial shade is highest of the box plots. Then I've got full sunlight with organic. Those are 2 different levels on these. That's kind of interesting. And then I've got organic partial shade, and then full sunlight with synthetic is the lowest. Okay, so I don't really see a very clear trend going on with this. Okay, now I'm looking at this and I'm like, wow, what's going on? Now another thing to notice is that, relatively speaking, these look like they have about the same spread for all 4 box plots. Okay, so something might be going on. Let's keep going. All right, so let's go ahead and take a look. If I want to be able to do a hypothesis test, I'm definitely going to want to have the means going on. And so I can see what the means are by aggregating. So I'm using the pivot table method here. I can also get the same table or the same pandas data frame by using the pivot table function. All right, so sorry, this is the pivot table function. This is the pivot table method. You notice I get the same results, slightly different. Do whichever one you like more. And now I'm going and I'm just reorganizing this into another format, getting the same computations, but in a long format. Each of these have different uses for them, depending on how I want to analyze, whether I want to do a heat map or maybe a line plot, something like that. Now, you'll notice that I've got 20 observations for each distinct level, and I'm focusing on the mean of that. Why am I focused on the mean? Well, because I want to do a parametric test, if that makes sense. I didn't see any skewness, so I would want to go a little bit deeper with histograms, check the distribution, check that it looks normal. I know it's normal because I generated it, but in real life data, I would go and I would check it. Now, here's a heat map to show where do we have extremes. All right, so we see the more extreme values are not on one side or the other or top or bottom. And so this is kind of interesting. If I saw both blue on the bottom, both red on top, or both blue left, both red on top on the right, or some variation of that, but like next to each other, for the blues next to each other on the reds, that would be indication that one of the covariates has a larger impact than the other. Now, I have a decent sample size for this, and so that's an indication that maybe there's an interaction going on. So let's go ahead and do a visualization showing this. So remember, I've got 20 data points went into this mean, 20 data points went into this mean, 20 data points went into this mean, 20 data points went into this mean. All right, so I see that I have non-parallel lines. That is an indication that there might be interaction between fertilizer and sunlight. If I see approximately parallel lines, then that is an indication that we do not have interaction between the two. Now, when I say approximately parallel, they don't have to be exactly parallel, but close to it is fine. Now they don't actually have to cross. There can be interaction where one line's completely above the other. All right, so interactions show how the effect of one sample varies with the level of the other. Significant interactions implies that factors are not working independently. And to visualize interactions effects, we create the line plots, such as this one that I created. Nearly parallel lines indicate no interaction between the factors. Non-parallel lines, and so the more they look like they're crossing, or would cross if you continue the line, indicate an interaction between the factors. And honestly, this is a subjective evaluation, but this is in a way for us to visually come up with evidence. All right, so just to reemphasize some things, factorial designs versus randomized block designs. Factorial designs handle multiple treatments and interactions. They analyze complex multivariable effects and may need a lot more subjects to pull off because of all the distinct levels. Randomized block designs group similar subjects, control within block variance, the variance that is coming to us like out of the box for our subjects that we don't have influence over, and each treatment tested within each block. All right, so now for your homework, I want you to perform a two-factor analysis experiment with paper helicopters, just like we talked about previously. Choose two factors that have two different levels, and so this means that you'll have 4 distinct paper helicopters. Design your experiments in the same manner as previous assignments. All other features of your paper helicopter need to be exactly the same. We want to limit this to a relatively easy experiment. Record the fall times from 3 different runs on each. So I'm going to make 4 different helicopters. I'm going to drop each one 3 times. The order needs to be random. And I'm going to analyze the results and make sure that the entries on your data frame reflect the aspects of your paper helicopters and your experiment. All right. Well, that's all I've got for you. Life is short. Do math.